I want you to be real comfortable with these graphs. That's why I was kind of hoping more of you did this work. We talked about your domains and your ranges. You know the sheet that I gave you where you're defining everything? These are all parts of your function. So we talked about your domains and your ranges. Then we got into this, and we talked about your increasing, your decreasing. This is where you're looking for your absolute minimums, your absolute maximums, your relative minimums, your relative maximums. You see that kind of tying into that sheet with all the definitions on it? That's how we describe your function. So we kind of piece this together right now. So from here, we're going to add a little bit more to it when we describe these things. Now, the rest of this also had your max and minimums and your increasing, decreasing. I find increasing, decreasing to be the hardest one because you're watching your value of your y, but you're talking to me the value of your x's. So here's a graph, and we're going to spend a lot of time on these coming up. This is a cubing graph. Your highest index is 3. Your highest exponent is 3. And your graph will come from here, increase, increase, till I hit this point. Decrease, decrease, till I hit this point. Increase, increase, till I hit this point. Up here, it just keeps on going. These are your 2 points you have to know. One is your relative max. Your max is way up here, it's definite. So we still do your max on your calc, number 4. To the left, to the right, find your max. This guy is your min. It's not your absolute because this guy keeps on going. It's your relative min. Again, left, right, get your min. These are your most important pieces up right here. Those are the only pieces you have to know for increasing, decreasing, wherever it's turning. So you're on your roller coaster, increasing, increasing from negative infinity to negative 2. It stops at that x. Then it's going to decrease when x is negative 2. It's going to keep decreasing your value of y until your x gets to 1. Then from 1, when x is 1, to infinity, your y is going to be increasing. So you have 2 increasing segments, which we join with the little u in the middle. But your max and your mins are really important, because without your max and your mins, you can't get your intervals. 39 again is a radical. Now remember, when it's hard to see, if that minimum is hard to see in here, because on your graph it's going to look like it's sitting at that line, it's going to look like it's going like this, you're not going to see it, change your window. Zoom your window into this. Don't use a zoom, change your window, but zoom it in this way on your window. Go to plus or minus 1 for both of these. Or go to plus or minus 2. It's still big enough. And now you'll be able to do your minimum. Remember when it doesn't work out, when it's irrational, we go 3 decimal places. That's another thing that's hard to get a grip on. Because we're always rounding to the tens, to the hundreds. This is 3 decimals. It's exact as we can go without having to go too far. So again, you're increasing from this point up, you're increasing. Find that point. From 0 to this point, you are decreasing. A very, very small section of decrease. It's a little tiny hook. Were you able to get this? If you didn't, are you able to see it? I need you to be able to see this. Okay, 41 is a nice little parabola. And we have to find the turning point. You can find it on your table. You need these. Or you can do it using your minimum point. This is an absolute minimum because it's absolutely the lowest point there is. If it's relative, that means we have an absolutely more minimum. You need that point, measure from your x. You're decreasing, your y is decreasing until it hits this x value, and then it stops decreasing. Then from that x value, it keeps increasing. questions on the increasing, decreasing? No? Okay, another part of your thing that you have to do is the odds and the evens. And the odds and the evens usually give everybody a little bit of trouble also. So we're going to work your odds and your evens today. And then we're going to do a couple more graphic complexities. Now, I like this little worksheet because it's cute and it's fast. It's cute. Okay. If it's odd, we said we should be able to replace the x with a negative x, and it should come out to be the same exact thing. If it's even, we should be able to replace the x with a negative x, and it will come out to be the original function. We also remembered that this has symmetry with respect to your y-axis. Because when you reflect over your y-axis, from this point to this point, say this is 1, 5, what's this point over here? Negative 1, 5. So it's saying xy will just negate the x, but the value of y will be the same. That's our rule for our reflection over the y-axis, and it makes sense when you look at this function. If it's odd, when we replace this, I know it's the same color, but that point is horrible. It's going to come out to be the exact opposite of this function. And odd has a reflection through the origin. If I take this point 1, 5, and I reflect it through the origin, what should that point be? Negative 1, negative 5. So our rule for a reflection through the origin is take your xy. If you negate your x, you negate your y. So your function is, your value of your function is negating as well. Now we said that's nice. We can graph this and we can visualize is there a reflection over the y? Is there a reflection through the origin? You can even look at your table and see it. But algebraically, we have to solve it. So we're going to take this function and we're going to substitute in a negative x. Be careful if you're squaring. Okay, and resolve this. When we square a negative, we get a positive. This one's not squared, so a negative times a negative, positive. This last term, we don't change. Now, does that match the original? No. So this is not even. It's not even. So check for an odd. To check for an odd, one of two things. You can look at every term to see if it's the opposite sign. So, oops, 5x squared is the same sign. The positive 4x is the opposite sign, but these two terms, not the same. I mean, they're not. They're the same as the original. Another way to do this is to factor out a negative 1. If y is going to become negative, it's right here. And then look to see in the inside if this is the exact same as your function, which it is not. So this is not odd. If it's not odd and it's not even, we just say neither. We say neither. Okay? Make sense? All right, let's try another one. See where I can put this. Check out number 2. Okay, we can graph this. This is a cubic function. We can look for symmetry, or we can use our rule. Negate the x. when you raise to an odd power, that negative becomes a negative. And a negative times a negative, a positive. Is this the same as the original? No, this is not even. So let's factor out a negative 1. If I factor out a negative 1, this guy's positive. If I factor out a negative 1, this guy's negative. Is this the same? Yes. And therefore, my y is going to be negative. This is odd. Now let me show you something interesting when you graph this. Watch what happens when you graph this. You can kind of tell that it's the same, but a nice way to tell is to pick one of these points up here and see if it reflects through the origin. So go to your table and pick a point, 365. If it reflects through my origin, it should be negative 3, negative 65. So I come here, and there I am, 69. Negative 3, negative 69. Both of them were the same with opposite signs. See it? So that shows me a reflection through my origin. So you can look at your graph, but you have to show it algebraically. So you guys try 3 and 4. Try 3 and 4 and see what you come up with. You can see a little pattern with the evens. When the evens get squared, they stay the same, right? That's the exact same as the first one. So this guy is even. You should see symmetry over the y-axis when you graph this. What do we get for this one? Neither. Okay, now this is what you're going to notice too. Odds and evens can't behave the same way, right? So when I replace this with a negative x, the odds will behave the same, but the evens won't behave that way. The odds will cause this sign to change. Cause this sign to change, but not the evens. So now you're not the same as the first one, and you're not all opposite signs. So this guy is a neither. Good? You can kind of see that difference? All right, let's try one more. Let's do number 5 together. Okay, so we're going to replace this with a negative x. Be careful of the way you replace it. It's within the parentheses. So this again becomes x squared plus 9. Is it the same as the original? Mm-hmm. Therefore, even. Therefore, it's even. Okay? Now, it's a radical, it is one arm, but there's a quadratic under your radicals. Remember when you did your quadratics and you looked for your domain restrictions? Watch that, this makes sense. When you take this one, okay, it's going to come out nicely, but you'll be able to see that it would come out on both sides. You'll see the two arms spreading out. So is everybody okay with this? You're going to finish this up, and today we're going to just sketch and describe another one. And you guys better make sure that you do this tonight. All right, so we're going to sketch this guy. And you're going to put it in your calc for me and sketch. You see the negative in front, so it's behaving like a parabola. It's over and down. Turning at this point, my pen is flip flop. This is at the center. These are both the same size. Yeah. Anytime anybody moves that table, my pen will go. Alright. So we can tell right there that it's even. That's a heart. It'll be on this side instead. Okay. Now, domain. What's the domain for this? We're going to describe all the pieces to this using your sheet that I gave you. Domain.
Negative infinity to 0.
Good. All round numbers. Negative infinity to infinity. Can I tell the range yet? Not yet, right? I need to know which point. The maximum. Is this an absolute maximum or a relative maximum? Absolute. This is an absolute maximum. And we want to see if they're both absolute maximums, if they're the same. If one is different than the other, then we only have one absolute. But because you see symmetry already, don't they both have to be the same x values and both same y values, which is what we're looking at for its maximum? So do a maximum, and shortcut, I'll show you a little shortcut for this. Do the maximum of this graph. Alright, watch. I'm going to do a maximum on the left-hand side. Absolute maximum. Relative max and absolute, we do the same way on the calculator. So I'm going to bring my little flash above here to the left of it, maybe. Okay. I'm going to bring it to the right. So this little arrow is starting to look. Now goes to the right. And there's my second arrow. It's going to come down here and look for my maximum. So I guess, and there's my maximum. It's got a decimal. So we're going to round it to negative 1.414. Now, if I want to know if this is the same exact, I could look at my table. But I really can't see negative 1.414 in my table, right? We're going through decimals. So if I do this, I can do this. Second calc, give me a value, and say 1.414, and we should come real close to this. And look how close we are. Isn't that other guy 4? Wasn't it 4? We're not exact because we rounded. But that's another way to see the symmetry. If it was a nice number like negative 2,2, I could look at my table and see positive 2,2. But because this is irrational, I can kind of do a calc and do a value. Can everybody do a value on theirs when you're looking for a number? When you're looking for any number, say I want to see if that's my 0. If that really is my 0, I'll say when x is 0, what is y? Oh yeah, y is 0. I can see that by doing a count on that and pick a value. So that's kind of another helpful little tool. So this is your negative 1.414, 4, and this is your positive 1.414, 4. You have to go 3 decimals. Once we know its absolute maximum, can we find its range? Negative infinity to 4. And I'm going to close bracket because I can use 4, right? Okay, now we've got to find an increasing, decreasing interval. So I'm coming along my roller coaster from negative infinity and I stop at this x point. This is an increasing. I stop at that x point. Then at this x point, I'm decreasing my value of y to that x point. Then at this x point, I'm increasing my value of y to that x point. So I loop another segment. And then after that, at that value of x, I'm decreasing to infinity. Now, you told me the domain was all real numbers. I should see all my segments here. Negative infinity to 1.414, 1.414 to 0, 0 to 1.414, and then 1.414 to infinity. I should see all of them accounted for. Okay? Now we've got our max. Do we have any relatives here? Do we have any relative mins or maxes? We did it by your calculator, but this guy right here, there's your relative. We did it on your calculator. I just didn't put it on here. This is your relative min. And I just did your 0 because it looked like it was at the 0, so that's why I put the extra 0 in there to make sure it was a 0, 0. Okay, let's do your intercepts. When x equals 0, when y equals 0. When x equals 0, I want to know where does it cross y. Yeah, I can tell, but I've got to still do it algebraically. So I'm going to take this equation and plug zeros in for x's. And that does give me a 0. And here my calculator confirms that. Now my y equals 0 will tell me where are my intercepts, where are my solutions, my real zeros on my x-axis. So I substitute in y of 0, and I have to factor this. So what's a common factor I can take out of that? Okay, let's take out the x squared, and we're left with negative x squared plus 4. So this guy right here, when you take the square root of 0, this is what causes this to bounce off your x-axis. This is called a double root. And we're going to learn more of this. Our highest exponent should give us how many zeros we have. I'm a little bit short, because this guy's a double one. Then this, x squared is equal to 4. Take the square root. X is plus or minus 2. You can do your perfect squares as well. Those are all your x-intercepts and your y-intercepts. They have to be done algebraically. I know you can check them with your calc-al, you can check them in your table, but check them this way first. Lastly, odd even. Substitute in a negative. And this comes out to be exactly the same as it was. So this guy is even. And don't we see symmetry over the y-axis? Right? We see the symmetry over the y-axis. Okay, for homework, you're going to complete both.